Hi everybody. In this lecture we're going to talk about definitions and terminology for differential equations. So the goal of a differential equations course is to learn what differential equations are and eventually how to solve them. But before we can talk about solution methods, we have to talk about some of the definitions and terminology so that we're able to select the correct method. So we're going to start with the definition. An equation containing the derivatives of one or more dependent variables with respect to one or more independent variables is said to be a differential equation. So if you think back to calculus, you learned how to take the derivative of a function, something like dy dx. Well, dy and dx, those are called differentials. So that's where the term differential equation comes from. For dy dx, typically the numerator represents the dependent variable, so in this y would be our dependent variable, and the denominator is the independent variable, so x would be our independent variable. So again, dy dx is our derivative. It's made up of those differentials, dy and dx, and so you can think of any equation that contains a derivative as a differential equation. We need to be able to classify our differential equations in order to pick the appropriate solution method, and there's several different ways to classify differential equations. The first is classification by type. So the first type of differential equation we may encounter is an ordinary differential equation, or ODE. So an equation that contains only ordinary derivatives of one or more dependent variables with respect to a single independent variable will be an ordinary differential equation. So for example, dy dx plus 5y equals e to the x, or the second derivative of y with respect to x minus dy dx plus 6y equals 0, or dx dt plus dy dt equals 2x plus y. Notice for each of these examples, all of the derivatives are taken with respect to a single variable. The first two examples it's taken with x, the third example it's taken with t. Also notice that when we write our derivative here, we use the standard d to represent the derivative, and that's what signifies it as an ordinary derivative. The other type of differential equation we can have is a partial differential equation. And so definition says an equation that contains partial derivatives of one or more dependent variables with respect to two or more independent variables. So some examples of PDEs is the second partial of u with respect to x plus the second partial of u with respect to y equals 0, or the second partial of u with respect to x equals the second partial of u with respect to t minus 2 times the first partial of u with respect to t. Alright, so notice in all of these equations we have the partial differential operator, that thing that's kind of a cross between a d and a 2, and the variables, the independent variables, aren't all the same. So in our first equation we have an x and a y, and our second equation we have an x and a t. So these signify that this could be a partial differential equation. Now in this differential equation course that I'll be recording lectures for, we won't be going into partial differential equations. We'll only be looking at ordinary differential equations. The second method that we have to classify our equations is classification by order. So the order of a differential equation is going to be the order of the highest derivative that you see in the equation. And just as a reminder, if you just have your dependent variable, say y, that's the 0 order. Dy dx, or y prime, that would be our first order. The second derivative of y with respect to x would be our second order. The third derivative of y with respect to x would be our third order, so on and so forth. So as the number on your derivative goes up, the order goes up as well. Another way that we can classify differential equations is by linearity. So our requirement here says an nth order ODE will be linear if the dependent variable y and its derivatives, y prime, y double prime, all the way up to the nth derivative of y, are all of the first degree or have a power of 1. The second restriction is that the coefficients a0, a1, a2 of y prime, y double prime up to yn depend at most on the independent variable x. So that means that our coefficients can have x's and they can have constants, but they can't contain the dependent variable y. All right, and third, if our ODE is linear, it can be written in the form a sub n of x times the nth derivative of y with respect to x plus a sub n minus 1 of x times the n minus first derivative of y with respect to x. The order on the derivative will continue to decrease until we get to a1x times dy dx, and then plus a naught x times y, and then that'll be equal to some function g of x on the other side of the equation. All right, so some examples with linearity. Y double prime plus 2y prime plus y is equal to 0. This is a linear equation because it satisfies both of those conditions. Y prime, and y double prime all have a power of 1, and our coefficients, 1, -2, and 1, they don't contain y's in them. So this would be a linear equation. Similarly, the third derivative of y with respect to x plus x times dy dx minus 5y equals e to the x. This also would be linear because it satisfies those two conditions. Y dy dx and the third derivative of y with respect to x, they all have a power of 1, and our coefficients, so we have -5, x, and 1, they all are either constants or dependent on x. There are no y's in our coefficients, so this satisfies both components of the requirement, so this would be linear as well. All right, and so an ODE will be nonlinear if it's not linear. So if one of those requirements is broken, then that's going to create a nonlinear equation. So examples of nonlinear equations. So here, 1 minus y times y prime plus 2y equals e to the x. So if we look at y and y prime, they both have a power of 1, so they're both first degree. So that first condition is satisfied. But when we look at our coefficients, the coefficient of y prime is 1 minus y. Since that depends on y, that's going to break the second condition, which will make this a nonlinear function, right? And then the fourth derivative of y with respect to x plus y squared equals 0. So again, if we look at this, we look at y and the fourth derivative of y with respect to x, y has a power of 2 on it, so that'll break our first condition. So these are some examples of nonlinear differential equations. All right, so let's work through some examples where we want to determine what the linearity is and what the order is of the equation. So for our first example, we have x times the third derivative of y with respect to x minus dy dx to the fourth power plus y is equal to 0. So we want to find out what is the order of the ODE, and is it linear or nonlinear? And if it's nonlinear, we want to explain why. So take a minute, see if you can figure this out. What's the order of the ODE, and is it linear or nonlinear? If it's nonlinear, explain why. Pause the video if you need a little bit of time to work it out, and I'll talk about the example right now. All right, so the order of the ODE is going to be third order. Remember, order is just going to be the highest derivative that you see there. So the third derivative is the highest derivative. That's going to make this a third order ODE. And for the linearity, we look at those two conditions. So first, y and its derivatives have to have a power of 1. But if we look at that middle term, dy dx raised to the fourth power, that's raised to the fourth power, not to the first power. So that's going to break that first condition. So this will be nonlinear because that derivative of y is raised to the fourth power. Let's look at the second example. The tangent of y times y double prime minus the sine of x times y is equal to 2. And again, we want to find the order of the ODE and determine if it's linear or nonlinear. If it's nonlinear, we want to explain why. All right, so the order of the ODE, we're looking for the highest derivative that's there. So for this example, the highest derivative we see is the second derivative. So this will be a second order ODE. For the linearity, we look at our two conditions. Y and the derivatives of y have to have a power of 1. Well, that checks out for this problem. And then the coefficients of those terms have to depend on x or constants, right? Can only have constants or x in them. So if we look at the coefficient of y, that's sine of x, that's fine. But when we look at the coefficient of y double prime, of the second derivative of y, we have a tangent of y. And since that coefficient depends on y, that breaks our second condition, which means this will have to be nonlinear. So it's nonlinear because the coefficient of y double prime depends on y. All right, so now that we've talked about classifying differential equations, we can move on and discuss solutions. Ultimately, that's what we want to get to in this course, is we want to be able to find the solutions of our differential equations. And so in this section, we're going to talk about what a solution is and how we can show that something is a solution. So by definition, any function phi defined on an interval I and possessing at least n derivatives that are continuous on I, which when substituted into an nth order ODE, reduces the equation to an identity, is said to be a solution of that equation on the interval. So basically what this means is any function that produces a true statement when it's plugged into a differential equation is going to be a solution to that differential equation. And that kind of makes sense. If you think back to algebra, right? If you think back to algebra, you had 3x plus 1. And you could find, or you could be told, that the solution is x equals 2. Well, how would you prove that x equals 2 is a solution? You would plug x equals 2 in and say 3 times 2, well that's 6, and 6 plus 1 equals 7, so that checks out. When I plug x into the equation, it gives me a true statement. So the same thing is going to happen with differential equations. If you want to see if something is a solution to a differential equation, you'll take the required number of derivatives, you'll plug everything into the differential equation, and then you'll simplify. And if your simplification yields a true statement, then that's going to be a solution. So let's look at an example here. We want to show that y equals 6/5 minus 6/5 times e to the negative 20t is a solution to dy dt plus 20y is equal to 24. So our differential equation, dy dt plus 20y equals 24, has a potential solution of 6/5 minus 6/5 e to the negative 20t. So in order to show that this is a solution, we need to plug it into our differential equation. Our differential equation has both y and dy dt in it, so we need to first take the derivative of y. We need to find dy dt. If we take the derivative of y, the derivative of 6/5 is going to be 0, and the derivative of 6/5 times e to the negative 20t will be 6/5 e to the negative 20t times negative 20. If we simplify that, negative 6/5 e to the negative 20t times negative 20, we'll get 24 e to the negative 20t. All right, so we have our y, we have our dy dt. We're going to take both of those expressions and we're going to plug them into the differential equation. So if we do that, we'll get 24 e to the negative 20t plus 20 times 6/5 minus 6/5 e to the negative 20t equals 24. We'll distribute throughout the parentheses. So this will become 24 e to the negative 20t plus 24 minus 24 e to the negative 20t equals 24. On the left-hand side, you can see that the 24 e to the negative 20t and the minus 24 e to the negative 20t will cancel each other out, so we'll get 24 equals 24. So that is going to be a true statement, so that is true, which means that this would be a solution. As you're working through your differential equations course, you may come in contact with different types of solutions. So we have both explicit solutions and we have implicit solutions. And so both of them will be solutions to the differential equation. The difference is how they're expressed. So by definition, a solution in which the dependent variable is expressed solely in terms of the independent variable and constants is going to be an explicit solution. And a relation, g of xy equals 0, is said to be an implicit solution of an ODE on an interval I, provided that there exists at least one function phi that satisfies the relation as well as the ODE on I. So an explicit solution is a solution that is in the form y equals, and then some expression that only contains x's and constants. So you can think of an explicit solution as a solution that has been solved for y. An implicit solution, on the other hand, is going to have your y's and your x's mixed up. Y is not going to be all by itself. All right, so for example, if we have x squared plus y squared equals 4, is that going to be explicit or implicit solution of the ODE dy dx equals negative x over y? So again, an explicit solution is one where y has been solved for. So y is all by itself. That's not the case here. We have x squared plus y squared equals 4. So that means this is going to be an implicit solution. All right. Note that the interval of existence for a solution is going to be the same thing as the domain of that solution. You should also note that if you have x squared plus y squared equals 4, even though that's an implicit solution, we could use algebra to solve for y and obtain an explicit solution if we needed. Now, typically that's not going to be necessary when you have an implicit solution. That's going to be a fine, that's all that you need. But if the question specifically asks for an explicit solution, note that you should be able to solve for y. Another type of solution that we're going to find, whether it be explicit or implicit, is going to be a family of solutions. And so recall when you were taking calculus that when evaluating an indefinite integral, you would often get a constant c added to the solution. All right, well, similarly, when we're solving a differential equation, we usually obtain a solution that contains arbitrary constants, c sub I. And any solution that can be produced by varying those constants is going to be a member of the family of solutions. All right. If you don't have any arbitrary constants in your solution, if the solution is free of arbitrary constants, then that's going to be called a particular solution. Okay, so for example, we want to verify that this family of solutions is a solution to the ODE. So the second derivative of y with respect to x plus 5 dy dx plus 6y is equal to 2x plus 3. And the solution they give us is y equals c1 e to the negative 3x plus c2 e to the negative 2x plus 1/3 x plus 2/9. All right, so notice our solution has arbitrary constants. We have c1 and c2, and so we can generate an infinite number of particular solutions by varying the values of c1 and c2. But for this problem, what they're asking us to do is verify this family. So to verify, we want to plug it in. Notice that our ODE has y, dy dx, and the second derivative of y with respect to x. So let's go ahead and find dy dx and the second derivative so we can plug those in. So dy dx is going to be negative 3c1 e to the negative 3x minus 2c2 e to the negative 2x plus 1/3 plus 0. And then the second derivative, if we keep going, the second derivative is going to be 9c1 e to the negative 3x plus 4c2 e to the negative 2x plus 0. So now that we have our y, our dy, and our second derivative of y, we can plug those into our differential equation. So the second derivative of y plus 5 times the first derivative plus 6 times y equals 2x plus 3. So again, we plug in those values we found. So the second derivative of y was 9c1 e to the minus 3x plus 4c2 e to the minus 2x. Our first derivative of y was negative 3c1 e to the negative 3x minus 2c2 e to the negative 2x plus 1/3. And then y was c1 e to the negative 3x plus c2 e to the negative 2x plus 1/3 x plus 2/9. So we plug those in. Now we're going to simplify. So we're going to distribute throughout our parentheses. So we'll get 9c1 e to the negative 3x plus 4c2 e to the negative 2x minus 15c1 e to the negative 3x plus 10c2 e to the negative 2x plus 5/3 plus 6c1 e to the negative 3x plus 6c2 e to the negative 2x plus 2x plus 4/3. So we distributed the 5 and the 6 throughout their parentheses respectively. Now we're going to combine our like terms. So we look at our c1 e to the negative 3x terms. We have 9 minus 15 plus 6, so those will cancel out. We have c2 e to the negative 2x terms of positive 4, negative 10, and positive 6. So again, those will cancel out. For our x terms, we just have 2x, so we get 2x. And for our constant terms, we have 5/3 plus 4/3. So that's going to give us plus 5/3 plus 4/3, which will be 9/3. And 9/3 simplifies to be 3. So we get 2x plus 3. And that's what we were supposed to get. So this shows that that is a solution. So that checks out. This is a solution to the differential equation. All right, so here's another example. We want to find the value of m, which is going to make y equals e to the mx a solution of the differential equation 5y prime equals 2y. So again, if it is a solution, that means when we plug it in, we get a true statement. So we have 5y prime equals 2y, and we want y equals e to the mx to be our solution. We'll start by taking the first derivative. So our first derivative will be m e to the mx. And again, if this is a solution, then when we plug these expressions in, it'll give us a true statement. So we want to find out what value of m would make this a true statement. So we get 5m e to the mx equals 2e to the mx, and we can solve this equation for m. We'll divide both sides by 5e to the mx to get m equals 2/5. So m equals 2/5 would make this a true statement. That would make this a solution. All right, the final thing we're going to cover in this section are systems of differential equations. All right, so sometimes we're going to see equations paired together in twos or threes. So a system of ODEs is two or more equations involving the derivatives of two or more unknown functions of a single independent variable. So for example, and this time we want to verify that these are solutions to the system of ODEs, we have the system. The second derivative of x with respect to t equals 4y plus e to the t, and the second derivative of y with respect to t equals 4x minus e to the t. All right, so this is a system of equations because it's two differential equations that are paired together, and oftentimes when you see this, they're going to be dependent on each other. So our first equation has x and y in it, and the second equation has x and y in it as well. All right, we want to show that x equals the cosine of 2t plus the sine of 2t plus 1/5 e to the t, and y equals negative cosine 2t minus sine of 2t minus 1/5 e to the t. We want to show that these are the solutions to the system. All right, so we're going to use the same approach that we've done before. However, when you're dealing with a system, you have to show that both equations are satisfied, so both equations are true. So we need to find the second derivative of both of these. So the first derivative of x is going to give us negative 2 sine 2t plus 2 cosine 2t plus 1/5 e to the t. And then the second derivative will be negative 4 cosine of 2t minus 4 sine of 2t plus 1/5 e to the t. And then for y, our first derivative will be 2 sine of 2t minus 2 cosine 2t minus 1/5 e to the t. And our second derivative will be 4 cosine of 2t plus 4 sine of 2t minus 1/5 e to the t. So now that we have x, y, and the second derivatives, we can plug in the pertinent expressions to our differential equations to see whether or not they're true. So let's start with the second derivative of x with respect to t is equal to 4y plus e of t. If we plug things in, our second derivative is negative 4 cosine 2t minus 4 sine of 2t plus 1/5 e to the t. And then on the other side we have 4 times y, so 4 times negative cosine 2t minus sine of 2t minus 1/5 e to the t, and then plus e to the t. If we distribute the 4 on the right hand side, it becomes negative 4 cosine 2t minus 4 sine of 2t minus 4/5 e to the t plus e to the t. And then if we combine those like terms, negative 4/5 e to the t plus e to the t, that'll become a 1/5 e to the t. And so we can see that both sides of the equation are the same. So this verifies that that's the solution. This shows that things are true. But remember, you have to do this for both equations. This isn't enough. We haven't finished yet. We need to look at the second equation as well. So the second derivative of y with respect to t equals 4x minus e to the t. I want you to verify the second ODE. It should follow along the same lines as the first example, but I'm going to leave this as an exercise for you to verify.